All right. Okay. I think you should get going. And for people in the room, can you kind of put your name because we want to keep track of the attendance. Thanks. All right. So yeah, since I'll be presenting in the room, so I'm going to stand up. So you may feel like the video, the angle of the video is a little bit strange, but yeah, but I'm just plowing through. All right. Again, good afternoon, everyone. So welcome to this seminar. As Nes mentioned, this is a seminar on federated learning. Okay, I'm an assistant professor in the ECE department. So today I'm going to talk about some of our recent pretty interesting work regarding how to mitigate data and system heterogeneity in federated learning, and particularly how we are going to mitigate the impact of fat tail noise in FL. Okay, so I feel like many of the people online are already pretty familiar with federated learning, but since this is a department seminar, and I'm not sure everyone is familiar with the background, so the talk will be kind of organized into 3 parts. So the first part will be on an overview of federated learning, and for those of you who are not familiar with this topic, hopefully this will kind of bring you up to speed, and maybe even better, if you are interested, you can also pursue this research direction in the future. And then in the second part of the talk, I'm going to talk about how to deal with the system heterogeneity, and the last part will be on how to deal with data heterogeneity. Okay. So let me just start with some like a very high level, 30,000 feet overview of our, the technology evolution history, right? So you can see in this picture, as a human race, we have gone through several phases in our technology advancements, right? So we started off from like a very basic tools. Actually, a few days ago, I just rewatched the movie 2001: A Space Odyssey, a classic movie. We start with a bunch of monkeys, right? If you remember, and then of course, things get very slow until around 70, 80. We enter the industrial evolution, right? And then this age is all about transforming energy. So now instead of using our muscle, now we leverage all kinds of machines, right? And then and all the way up to in the 1970s, with the advancement of computers, right, and particularly personal computers, we are entering the age of transforming information. Okay, now this is still ongoing up to right now. But of course, we're kind of at the verge of transforming information and kind of moving to the next stage, which is transforming intelligence, right? And particularly artificial intelligence. So, but looking back a little bit of where we are coming from, right? So we have seen tremendous success of the internet, right? Of course, this is some fancy pictures, but one of the key reasons of the success of internet is that it allows us to basically communicate and share information anytime, anywhere, right? Of course, like holding this seminar, people can join the seminar all over the place, online, offline, whatever you want, right? Now, we actually wonder, could this, continue to hold in this kind of intelligence age, right? Or the learning age. So basically, the vision is that can we do learning anytime, anywhere, or can we perform machine learning at will, right? That's the kind of like a pretty high level visionary question. And of course, the answer is yes. But to kind of see where we are coming from, let's just kind of quickly review the traditional learning pipeline, right? So of course, this is still going on. This is kind of like a traditional training of machine learning, right? So basically, you can see, you have lots of data coming from everywhere, and then all these data will be collected and aggregated into some centralized data warehouse, and then going through some like a pretty heavyweight supercomputer, training all that stuff, and eventually we have some machine learning models which could claim to have some intelligence, right? Like for example, I feel like many of you have heard about ChatGPT these days, right? And I also play with it a little bit, and it's actually scarily good. Yeah, I'm a little worried at some point we'll be losing our jobs pretty soon. But anyway, but this is the way people do learning, right? We do the learning in a rather passive way. You have all the data, and then these raw data will be collected, and then the learning will be performed at a kind of like a centralized spot. In other words, as the users, we don't have any control over how these learning can be done, right? Now, let's get to federated learning. Basically, with federated learning, we're kind of changing the paradigm. Okay, so instead of surrendering our data and maybe our privacy along the way, right? And then you let some guy do the learning. Now we would actually keep the data local, okay, in federated learning, and then we only share a limited information with the entity that is performing the learning. And eventually, these learning can the learning model will be also sitting at the local, and then eventually with certain technologies, we can even personalize these learning model at each client. Okay, and so you can see that in this way, the users become much more proactive, and then hopefully in the end we will do something like learning at will. Okay, so eventually I'll get to this point. But of course, this is still a wish list. It's not the fact yet. Okay, but so to give you guys a very basic introduction of federated learning, I feel like maybe perhaps it's the best way is to start from the root. Okay, so essentially what we are calling machine learning these days are in fact just solving a mathematical optimization problem in one form or another. Okay, so you can see that the problem can be written in general in this way. You want to minimize some effects. This is actually called a loss function in machine learning jargon. The loss function is basically measuring your like a learning model output, the discrepancy between your learning model output and some label data, basically. Okay, and the loss is measuring the gap between these two, and you want to minimize the gap, right? So if you can train a model that can emulate the label data, then that's what you call learning some stuff, right? So basically, we are trying to minimize this loss function, and of course, this X is representing the learning model parameters, and this C is representing the training data, including the features and the labels. Okay, so of course these data are drawn from some underlying distribution. We sometimes you have some ideas, sometimes you have no idea about. Okay, now basically we want to minimize this optimization problem, and of course with the deep learning becoming so popular, you can expect that the X will be pretty high dimensional. Okay, some people call it over parameterized. So because of the high dimensionality of these problems, probably the only way to do it is to use some simple algorithm. So if you're familiar with some of the basic optimization, this is one of the most simple algorithm people use, called stochastic gradient descent, right? SGD. So now the algorithm itself is extremely simple, just one line. So basically, in each iteration, you draw a mini batch, BK, with this batch size also BK. Okay, and then you do this iterative update. The next iteration of the model parameter will be equal to this XK in the current iteration. Following some stochastic gradient step, okay? And then of course this is average over this mini batch. All right. So this is probably you wonder, these are all very simple, right? Why we spend time talking about this? Well, the reason is that this actually basically the foundation of all these kind of distributed or federated learning. So in this summation structure, you can see that actually I can decompose the summation which will be performed at different locations, right, by different computers. And then that's basically how you do these things in parallel. Okay, so you have a bunch of workers computing all these stochastic gradients in parallel, and then you have a server aggregate them together, and then eventually, you have distributed computing. Right? So okay, so this insight is actually the foundation of distributed learning, and actually federated learning can be viewed as one type of a distributed computation. Now, of course, there's still some difference, right? But federated learning, as I said a minute ago, so it's one type of a distributed learning, and therefore they share a lot of similarities. Okay. However, there's still some key difference. So in centralized, well, not centralized, distributed learning in a data center. Okay. So usually the data set can be assumed to be easily accessible by each computing unit in the system. Okay, and because of this reason, you as a theorist, you can sometimes safely assume that these data are well shuffled. Okay, and of course this may or may not be true, but sometimes you can argue this is the case. However, in federated learning, you can no longer assume these things, because the structure of federated learning actually looks like this. So of course you have a parameter server, you have a bunch of clients. The number of clients could be pretty huge, and you have but each client will hold a local data set. Okay? And the premise here is that these data sets cannot be shared, okay? Due to privacy reasons, due to security reasons, or simply due to high cost of communication. Right? You don't want to share these data. So because these data are all sitting locally, and therefore you cannot assume, these kind of well-shuffled data set, which implies IID distribution, all things like that. Okay? These are no longer true. Now, let me also give you guys a little bit historical perspective of federated learning. So the terminology of FL, federated learning, first appeared in this 2016 pioneering paper by people at Google. Okay, and then of course the first official paper, the first version of this paper appeared in AI Stats 17, but the archive version came out a little earlier. Okay, so the key motivation of FL is that the learning was focused on more on the mobile and edge devices collaborating to train a global model. Okay, and this is actually fitting our AI edge vision. And so because of that, there's no need to transfer client's data to the server so that you can preserve privacy. Now, of course, federated learning is a very, very popular topic these days. And in fact, according to some statistics, in the most recent NeurIPS happening in New Orleans last month, federated learning is the second most dominant topic across all the subfields of machine learning. Okay, it's a very active, ongoing research field. But in some sense, you can say that all these papers are dealing with the following challenges. First of all, as I mentioned earlier, these data sets are local, right? and you cannot assume they're of the equal size. Right? The data set size could be unbalanced. The data sets could be non-IID, and sometimes the number of devices or core clients in the literature, the number of clients could be huge, and since these devices are some edge devices, mobile devices, the communication capability of these devices could be pretty limited, and also the availability of these devices cannot be assumed, right, at all time. Right, for example, some devices like a cell phone, it could be power off. It could be charging, or the Wi-Fi is not available, things like that, right? So a lot of random stuff could be happening. Okay, and also roughly speaking, there are two major categories of FL. One is called cross-device, and the other one is called cross-silo. This is roughly based on how many devices the learning is dealing with. If you have lots of devices, it's called cross-device. you know, if you have rather fewer number of devices, then it's called cross silo. Okay, but these are relative. Don't read too much into the terminology. But roughly speaking, this is the typical numbers of what people meant cross device or cross silo. Okay, and also compare with the distributed learning, you can see that. As I said, these federated learning are usually deployed on the wireless networks, or some larger scale network. But the distributed learning usually are performed in a larger data center, something like that. And also, if we are talking about cross device, the number of devices could be up to 10 to the 10 sometimes, right? It's a huge number. But for cross silo, the number of devices is usually smaller. But nonetheless, for these two FL paradigms, you will always find data heterogeneity and system heterogeneity. Okay, so these are the central topics people are dealing with. Some applications of federated learning. I don't claim myself an expert in terms of all these applications, but these are nonetheless well known. For example, FL has been used in Google Gboard, like a smart keyboard. I'm not an Android guy, so I have no idea how good that keyboard is. But it is also used in Apple QuickType and even Hey Siri, okay, in Apple devices. Now for cross silo FL, it has been used in many applications as well, including some financial risk prediction, pharmaceutical discovery, electronic health, and medical data segmentation, smart manufacturing, etc., etc. Okay. Now, roughly speaking, in all federated learning algorithms, you have these major steps roughly in this sequence. Okay, so you start with some client selection, since sometimes there are so many devices, right? You cannot communicate or enlist all of them at the same time. So you have some selection first, and then you will broadcast the model to all these clients. Sometimes I would also like to call it workers. And then you let these clients do the computation for you, right? Typically, this means you ask these devices to compute some stochastic gradient or gradients, and then you will aggregate the result returned from these devices. Right? And sometimes you could even have some potential additional processing, like filtering out some malicious information. Sometimes some device could want to attack you, right? So you want to do some additional processing, and then you update the model. Okay, so that's the roughly speaking, that's the whole process. So as I mentioned earlier, right, FL is so popular. So you might wonder why. What's the fuss is all about, right? So, well, a quick answer is that FL is inherently interdisciplinary. Okay, so these are some of the areas where people are working on FL. So including, of course, machine learning, distributed optimization, people from operation research, people from security working on cryptography, differential privacy, and people from economics could work on fairness. People from signal processing could be worrying about how to do compressed sensing, crowd sensing, and of course, as a networking person myself, I also worked on some wireless networking issues related to federated learning, but all that kind of stuff. Okay. So in fact, many of the hardest problems in FL are at the intersection of all these different areas. So that's why the topic has generated so much interest. Okay, so as I also alluded to earlier, basically learning, you can view it as solving some mathematical optimization problem. Right? So that's the same in FL. In fact, this so-called federated average algorithm, Fed average, aka local SGD or parallel SGD, depending on which paper you're looking at. this algorithm is basically like a template, a basic template for federated learning. Okay? So, these are some basic notation. N represents the number of clients. M is the clients per round. T is a total communication round, and K is number of local steps. Okay. So here I want to use these two terminologies to clearly differentiate these kind of iterations. So like for the communication between the client and the server, I use this terminology called round. Okay. And this K, I will call it local step, but you can sort of think of them as some computation iteration. Okay. So the basic process is that first of all, at the server, you initialize some x0, okay, and then for each round, okay, from 1 to some capital T round, then the server will first select a subset of the clients, okay, assigned to this set ST, and then you ask these clients in this ST to do some computation in parallel, calling this subroutine called client update. Okay, and now let's jump into the client update. Basically, here the computation is very simple. Each client will get the model parameter from the server. This x0 is this x. Okay, and then each client will do some SGD style update, very similar to what I just talked about. Of course, you will allow them to do multiple steps. Okay? So actually, this is one of the key features of FL. If you only do one time, essentially it's the same as doing batch SGD. Right? The unique feature of FL is that now you allow them to do multiple local steps. Okay? And after this is all done, then you return this XK after K step, right? You have an XK, and then you return the result back to the server. Okay, now coming back to this line. And then eventually the server will do like an averaging operation, and you get to the next iteration. Okay, so that's the basic template. And of course, you can implement this algorithm in several different styles. So sometimes people, rather than feeding this XK directly, sometimes you can just feed back the update, the delta, okay, rather than feeding back the X for a lot of good reasons, which I'm not trying to get into right now. And sometimes you could even have some additional processing. You can compress the model to save communication costs, or you can do some other extra operations. Okay. Now let's this is like a very quick overview, a crash course on federated learning. Now let's get to our work, recent work on federated learning. So the first part I'm going to talk about is this so-called anarchic federated learning. This is a joint work with my student Haibo Yang, Xingzhang, Prashant, and myself, of course. It appeared in last year's ICML. So yeah, of course, Haibo is still at OSU, and Xing is he's one of my former students at Iowa State, and he's now with Meta. Prashant is a joint postdoc between myself and my friend and colleague, Professor Ming-Yi Hong at the University of Minnesota. Okay. And he's now a new assistant professor at Wayne State, 3 hours away from here in Detroit. Okay. So, all right. So now, yeah. So to talk about what we meant anarchic federated learning, so it would be good to just quickly go over again this kind of basic federated learning, right? So as I just mentioned, the learning is just this kind of optimization problem. You want to minimize this fx, which can be decomposed into the summation of all these local loss functions, right? This alpha is actually representing the proportion of each data set at each client, and then this di is the local data set. Okay. Now, so basically, all these current algorithms in FL can roughly be kind of characterized into these 3 major steps, right? Selection, computation, and aggregation. And in fact, if you look at these algorithms a little closer, you will see that the server will play a major role in all these FL algorithms. So that's why we call it server-centric. basically what we mean is that the server will do the selection. Okay, it dictates which client will participate, and then it will send out the instruction to all the clients. Hey, follow this kind of SGD update, or add a momentum, or you add a variance reduction, whatever you do. But this is dictated by the server again, and then you do the aggregation. This is clearly done by the server, right? So the server is very busy throughout the whole process. So of course, this makes sense because you could see that this kind of server-centric Fed average type algorithm has a lot of nice features, right? By saying server-centric, basically the server will do all these things. And another thing about server-centric Fed average is that we have the so-called linear speedup for convergence. Right. So for those of you who are familiar with optimization, please don't confuse this with linear convergence speed. It's not, okay? So it's still a sublinear convergence speed. So what we mean by linear speedup is that as the here you can see this capital M, that's the number of clients, okay? As the number of clients increases, then your time in training will decrease kind of inverse proportionally, okay? So in simple words, basically, if you double the number of clients in your FL process, then the training time should be shrink by half. Okay, so that's what we call linear speedup. Okay, so quantitatively, if you can show your algorithm has this kind of convergence rate, okay, which I will go to a little bit later, then you basically show that this algorithm has this kind of linear speedup. Okay, so that's one of the key benefits of all these server-centric type Fed average algorithm. However, there are also several major issues with this kind of server-centric FL schemes. For example, you could see some straggler issues. You could see some energy waste issue and some bias and fairness issue. Right? So let me give you some cartoon to clearly illustrate why this is the case. Okay, so let's take a look at this toy picture. Now here you have 5 clients, right? So supposedly, okay, so in this system, suppose that the server will pick, yes, all these 5 clients to participate in, for these 4 server, these 4 clients, 1 to 4, to participate in the training. Because of all these kind of preventing race condition issues, you want to log the system, okay? So that you want to ensure that the models are updated consistently. Now, maybe in this case, this client 1 and client 2 are doing job pretty fast. They are having stronger computation capabilities. So because the system is locking, right? This client 5 is basically cannot participate, right? Essentially, it cannot do this learning at will. Okay, the system will lock it out. Now, after these 2 clients perform the learning a little earlier, right? Then you could run into some issue like the following. So, for example, the client 3 could be running out of battery, right? It's just kind of dead. And server 4 here, I use like a watch. Right? Of course, it doesn't have to be a watch, but basically what I mean is that this is a very pretty slow device. Now you have some problem. So should I wait for these 2 clients, right? If you wait, then you kind of these 2 clients would drag you down, right? It will make the learning process very, very slow. But if you don't wait, right, then basically this guy will waste all the energy, all the computation resource to do the learning, and if you simply drop its result, then it's kind of you waste its energy, right? And it also causes some bias or fairness issue as well. So the problem is how to deal with that. Okay? So our solution is the so-called anarchic federated learning. Okay? So it sounds a little bit contradictory, right? How can you do federated and while being anarchic? But now let's just take a look at our anarchic federated learning. This is our general framework. Okay? So recall earlier in this kind of server-centric algorithm, you have the server and the client doing things in a alternating pattern. Right? So the server do something, the clients will do something, and then the server will follow up with something. Right? It's kind of like alternating. Now, the key feature in anarchic FL is that all things happen concurrently between the server and the clients. So for example, in here at the server, concurrently with the workers, the server is actually quite lazy. Okay, I just sit there passively, wait and until it collects some local update return from the clients until the server accumulated some enough number of clients result, and then after that, the server will aggregate the results from the workers and update the global parameter, following some server-side optimization process. So here I'm intentionally, I want to be vague intentionally. Okay, so later on I will kind of fill in the details in these steps. Now at the worker, again concurrently with the server. So once the worker decided to participate in the training, the worker will just pull the model with some current timestamp. Okay, so this is kind of important here. So we want the clients to write down the client timestamp, and then after that, the client will perform multiple local updates following again similar to the Fed average process, right? So you do some worker side optimization, and then the result will be returned to the server. And the result will be associated with the timestamp of the current model. Okay. If you want to do a little extra processing, you can do that, like compressing or adding some noise for privacy or things like that. Okay. So overall, this is a very general framework. Later on, I'll give you some specific algorithms under this kind of AFL paradigm. Okay. However, you can see that this kind of AFL scheme is much more chaotic, right, compared to the very consistent server-centric FL. So several fundamental questions naturally arise, right? So first of all, you may wonder, is it possible to design some algorithms that are convergent at all under AFL, right? This is not very clear. Right? Now, second question is that if the answer to the first question is yes, right, then you might wonder under what condition, right? You could actually expect that if this kind of anarchic behavior is too arbitrary, right? You may not be able to guarantee any convergence at all, right? So if I can establish convergence, then specifically under what kind of condition this convergence can happen, right? Now, even further, if the second question can be resolved, and also, the first question is also resolved, by the way, right? Then you may want to ask whether this kind of AFL continues to have this kind of linear speed up effect, right? Which is highly desirable, right? Actually, this kind of speed up effect is exactly the point you want to do distributed optimization, right? So with more clients, right, then you will save more time, right? That's the whole point of doing things in a distributed fashion. Well, turns out the answers to all these questions are yes, right? Otherwise, I won't be talking about things like in here. All right. So before we talk about the technical details, so actually, we want to understand the fundamental limit of AFL, right? So only if after you understand the performance limit, can you know how good your algorithms, the algorithm you design, how good they are, right? So so first of all, under AFL, we kind of derive some convergence error lower bound. Okay, so this is basically saying how good any AFL algorithm can perform. Right. So essentially, you see this big theorem here, right? So essentially, under some very common assumptions, like this kind of L-Lipschitz smoothness condition, unbiased stochastic gradient condition, and this kind of bounded dissimilarity, for non-ID data across workers, right? So all these can be reasonably assumed to be true in FL. Then we show that under general worker information arrival process, meaning that under anarchic FL, right, these worker results may not return at the same time, right? So, the result could arrive in a pretty random fashion. So basically, if you make no assumptions on the arrival process, then we can show that there exists at least a loss function, okay, such that for any algorithm, any stateless AFL algorithm, meaning that these AFL algorithms will not exploit any memory in the system. Okay, then for these algorithms, you can show that eventually there's a non-zero stationarity gap in terms of the gradient norm. Okay, so basically you cannot go to 0. Okay, there's a floor. Okay, in here, and this floor is basically determined by the variance of your stochastic gradient. Okay. All right, and now this is the lower bound. Okay. Now, after understanding the lower bound, then of course we would like to see whether we can design some good algorithms and how good they are compared to the lower bound. Okay, so the first algorithm we can think of is, of course, just it's actually pretty trivial. Okay, so we want to see whether we can slightly modify the basic fat average and see how it works, right, under AFL. So we call it anarchic fat average, or AFA. And then the first version is for the cross-device setting. Okay, so basically in here you can see at the server concurrently with the workers. Now in the Tth round, okay, in some update round T, the server will sit and wait until it collect M local updates. Okay, but these updates are not necessarily associated with the same model parameter. You can see there's a tau in here. These taus are representing the random delay. Okay, and of course you need in the end you need to assume some conditions on these random delays. Okay, but nonetheless these things are essentially asynchronous, and then you aggregate all these client feedback into this kind of a cap GT, and then you update this model parameter in this kind of again some SGD style update. Okay. Meanwhile, at each worker, and this is actually concurrent with the server. Okay, so once each worker decides to participate in the training, then the worker will retrieve the current parameter. Let's call it x mu from the server, and the timestamp. Okay, and set the local model initial value as the following, and then it will do the local updates with this KTI steps. So now this is another key feature of our AFL. So this KTI could be time varying, okay, across time. So in some round this could be some number, in another round could be another number, right? And this could also be device dependent. So each different device I could have a different KTI. Okay, so that's why we call it anarchic. You do whatever you want. Okay, so in here. Now after this KTI steps, you have this again some kind of a SGD style update. Now I want to point you to here. Right? You notice that this eta L and this eta, they are different. Right? They could be different. That's actually what we call two-sided learning rate. It's actually coming from one of our earlier papers published in iClear. This would allow you to actually enjoy a pretty large local update step. Okay, and the benefit of doing this is that this could significantly reduce your communication cost. All right, but I don't want to jump too much into that. But just so you guys know that with these two-sided learning rate, you can significantly reduce the communication cost. And if you are interested, you can go ahead and look at our iClear paper. All right. Now after that, the client will sum all these K steps result together with some appropriate scaling. And actually, this is this looks like a pseudo gradient, right? And we return the result back to the server, and then the whole thing will keep going again and again. Yeah. That's the anarchic version of fat average. Then we show that basically with all these basic assumptions, again, like a bounded maximum delay. Okay, basically you need to assume that the random delay has to be bounded, which is actually reasonable. Okay, and then with Lipschitz and Lipschitz continuous condition, unbiased stochastic gradient, and bounded dissimilarity and non-ID, all that kind of stuff. Then the alpha sequence of this AFA cross-device version with the general worker information arrival process will satisfy the following result. Okay, so it looks a little complicated, but basically this result is saying that the time average of the stationarity gap is upper bounded by this term. Okay, this term is like a vanishing term as t gets large, and the second term is a constant term that won't disappear no matter how far you go. Okay. Now, of course, that result is still pretty complicated. Now, just to help you guys make sense of it, we can derive some insights from that previous result. Okay, so basically, here, what this corollary is saying is that if these clients are not that anarchic, okay, and in the sense that they can agree on the ATL, they can agree on some local learning rate. Of course, this global learning rate is determined by the server. Okay, it's pretty easy. So now let's say they can agree on these things. Then the previous result implied the following stationarity gap. Okay, now you can see that the dominant term here is this 1 over square root of MKT. What it means that this is actually linear speed up. Okay, which is good. These two terms are a higher order term you don't need to worry about, and this is the lower bound, right? Remember, so basically this is saying that well, surprisingly, for the anarchic fat average, we can achieve the lower bound with the linear speed up feature. Okay, so that's the key message. Now the cross silo version is also pretty similar. In fact, the worker side code is exactly the same. The only difference is in the server side. Okay, so in the server side, the thing is that because in cross silo you have relatively smaller number of clients, right? Then the server can afford to memorize all the client information, the historical information. Then if in some round, right? If I only collect a subset of the clients, for those clients that who didn't submit their result, I can use some historical result in my memory to compute something like a sort of like a full gradient, but with outdated information. Okay. Now with that, you will update again the model parameter xt in this kind of SGD fashion, right? So the only difference is in cross silo you have memory. Now with that, we can show that again under all these kind of general kind of pretty general assumptions, then by choosing the global and local learning rates appropriately in the sense of all that kind of complicated conditions, then you can show that under general worker arrival process, information arrival process, the time average stationarity gaps satisfy the following result. Okay, so this still look pretty similar to the earlier one, but but under this cross silo setting. Okay, and again, assuming the clients are not anarchic in the sense that they can agree on the local learning rate and the global learning rate, then you have this kind of a stationary gap, right? Convergence rate. So now you can see that still we have this linear speed up effect, and better yet, this is actually not small m, this is capital M. Okay, so this is actually even better than the cross device version, right? Another big result is that now you can see that the lower bound is gone. Okay, so by leveraging the memory, we can actually get rid of the that sigma squared lower bound. Okay, all right, so so that's the result. So basically, or intuitively, this says that if you can leverage memory, then you're actually doing not that poor in this kind of anarchic setting. Okay, So now here are some numerical results to quickly show you how these, anarchic fat average algorithm will perform. Now we just use the, this kind of vanilla fat average as our baseline, right? Because in the general standard fat average, things are very happening in a very organized way, right? So you cannot expect our anarchic version to beat the standard version, right? But of course, because of that, we would like to see how far or how poor the anarchic version are, right, compared to the standard fat average algorithm. So here we want to actually the system is actually quite small. Okay, so just like a very small scale experiments. Here we have 10 workers, non-IID data set based on MNIST, a popular data set in machine learning community. So what we do is that we MNIST is basically describing numeric digits, right? So there are 10 types of digits. So we kind of separate these 10 digits and allocate these data to different workers, right? So this P representing how many digits each client has. So if each client has only one digit types of digit, then you can expect that the data sets are extremely non-IID. Or as this P gets larger and larger, and eventually if each client has all P is equal to 10, right? If P is equal to 10, then that means that the clients have all the digits, right? Then that means this is like an IID setting. Okay? So now you can see that when the data is extremely non-IID, both AFA CD and AFA CS are not performing too well. That's kind of expected, right? Since you have a very heterogeneous data. But surprisingly, when P is equal to 2, right, then you can see that all of a sudden, both AFA algorithms would perform pretty close to this basic fat average, right? Now, as this P gets larger and larger, now you can see that eventually they are all pretty close to the standard fat average, right? Which is a good thing. All right, so, okay, a quick summary. So in this work, we basically study this kind of a anarchic federated learning paradigm, and we kind of so this paradigm basically features two things. One is that it features this kind of loose server worker coupling. Okay, this allows the worker to learn anytime at will. Okay, and then so we basically show that this kind of anarchic, even the anarchic version of basic fat average could perform pretty well. Okay, if you can kind of somehow manage their anarchic behavior. Okay. All right. So of course, this is still ongoing. We currently are very, very interested in doing several extensions of this kind of anarchic federated learning. For example, we could study FL with more sophisticated objective, like instead of having like a standard mean minimization, we could do min max, we could do by level, blah, 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 right? Actually, I want to point out that for this min max FL, we have a recent work also appear in this most recent NeurIPS last month. But of course, that wasn't anarchic, but perhaps we can do an anarchic version as well. Okay? So we can also study fairness. We can also study, Byzantine resilient, all these kind of interesting topics in this kind of new anarchic FL paradigm. Okay? Now, let me jump to the third part. How many time do I have? Wow, a couple of minutes left. Okay, so I probably need to go a little faster. Okay, so so in the part 3, we're talking about fat tail noise. Okay, so again, this is a recent work with my student Haibo and Pei-Wen. So yeah, Pei-Wen is actually a pretty new student. I think this work was done in her first year. Okay, so all right, so this work is actually motivated by a paper. Actually, we study in our this course I developed last year, non-convex optimization for machine learning. So there's a paper talking about heavy tail noise in stochastic gradient. Right. So this is also a pretty interesting paper. Basically, this figure shows that well, in general optimization or learning, people usually assume that these noise in stochastic gradients are Gaussian or light tail in a sense. However, if you really, do some histogram, okay, and compare this with this is Gaussian noise, this is some alpha stable heavy tails random distribution, you can see that the noise in stochastic gradient, this is actually for RLXN on CFAR 10, okay. This actually looks much closer to heavy tail rather than light tail, okay. So that actually motivate us to study whether the same stuff can also happen in federated learning. Okay. Now, well, actually, the answer is yes. So here's a very simple experiment we try out. This is a CNN on CFAR 10. Well, what motivates us to study this kind of heavy tail or fat tail? It's actually coming from something called catastrophic failure in the community of FL. Okay, so catastrophic training failure means that something happened dramatically during your training process. Like on this figure on the right hand side, you can see that usually as you have more and more communication round or training rounds, right, the accuracy should kind of continuously continue to improve, right? But in here, you can see that sometimes once in a while this could happen, right? The accuracy suddenly dropped to to a very low value. Okay, and so actually this is not very rare. It happens quite. I wouldn't say it happens every time, but it does happen quite a few times in some of our own research in the past. So actually, when we examined the gradient norm, we can see that corresponding to this sudden drop in accuracy, there's a huge jump, a spike in the gradient norm. Okay, so of course we have no idea why this could happen, but when we saw that paper in terms of the heavy tail noise in SGD, we wonder could this kind of heavy tail noise or fat tail noise could be the culprit. Okay. Of course, these things cannot be said definitely. We can only do statistics and see how correlated they are. So on this figure on the left hand side, we tested two cases. We wonder actually the data heterogeneity would be the culprit of this kind of heavy tail or fat tail noise. So you can see that for the IID case, the tail of the stochastic gradient noise is very light, right? However, if you look at some non-IID case, you can see the tail is pretty heavy. Okay, and in fact, if you kind of measure this alpha index, basically that's the exponent of your kind of the sigma. Okay, there's kind of like a variance. It's not variance, but basically the bound of this alpha moment. Okay, so you can see that as this non-IID index P gets larger and larger, okay, the smaller P is corresponding to more non-IID data set. So you can see that this alpha value is actually decreasing, right? So even if 10, you don't see this is going to 2, right? So it's something less than 2. So if you have a alpha being 2, that's Gaussian. Oh, no, sorry, that could still be heavy tail, actually. But you have a bounded variance so that all the proofs will go through, okay, essentially in FL. But if you don't have this alpha equal to 2, if something smaller than 2, then all the proofs will break down. Basically, all the FL convergence proofs doesn't work, okay? So now with this alpha being so small, sometimes alpha is less than 1, you don't even have the mean, right? For example, you could have a Cauchy distribution, things like that, and then, the noise could be pretty ugly, right? So actually, when we measure these things, we've actually found that it's not that rare when you have a non-IID data set in FL. This kind of heavy tail noise could happen. Okay, of course, there's also some ambiguity in the literature in terms of heavy tail or fat tail. So here we want to make a clear distinction. We call those noise with alpha less than 2 as fat tail, and sometimes some heavy tail could still have alpha equal to 2, like log normal or Y-bool, these kind of things, they could still have alpha being equal to, okay? So we want to understand what happens if you don't have finite variance. So when alpha is less than 2, you don't have a finite variance. Right? So of course, the way we can think of immediately is to do clipping. Okay, this is actually not a new idea in machine learning. Clipping has been used to do a lot of other stuff, like actually some people even use clipping to do differential privacy and all things like that. But anyway, clipping is a very simple way we can think of, right? If you have a heavy tail, then you just truncate the the result you return from the client, right? Cut off the tail, and then you have something you expect to be lighter. Right? So basically, clipping is just a way to control the norm of some variable x, right? And this lambda is the parameter you can play with to do the control. Okay, and then based on this idea, we come up with two algorithms. One is called we call it fed clipping. It actually means federated averaging with two-sided learning rates and clipping. So for short, it's fed clipping. Actually, pun intended. Okay. Of course, when you do clipping, there are several possibilities. In this kind of a fed average type framework, so you could do it every round, or you could do it every iteration, local iteration. So actually, we have no idea which one is better. So we try both. Okay. So you can see here, this is the per round version, the PR version. The clipping is done after each round, right? After line 9. So you do this clipping in each round before you communicate with the server. Now this is a PI version, the per iteration version. So here this clipping happens in every local update. Okay. Now clearly the PI version is more computationally expensive compared to the PR version because you need to do it in every iteration. Now, yeah, I don't have time, so I'll just quickly skim through all these things. So for the PR version and the PI version, we proved their convergence rate guarantee under non-convex and strongly convex cases. Okay, so yeah, so these are, yeah, I think let me just keep all these big boxes. Let me get to this table, okay, which summarize all the convergence rate results. So basically, yeah, you can see this is the lower bound we proved for FL with fat tail noise, okay, alpha less than 2. And we compare the result of our fat clipping, both PR and PI, with this lower bound, okay? So now the first observation we can see is that for the PI version, they are all lower bound matching, okay? So everything inside the red box, they're all lower bound matching under both strongly convex and non-convex cases. However, for the PR version, okay, you can see that well, the result in terms of the T dependence, the convergence rate in terms of T, they are still tight. Okay. However, the dependence on the K is the number of local steps. They are not tight. Okay. There's a gap, and actually this makes sense, right? Because if you are doing clipping relatively lazy, right, then you don't expect, you can manage those fat tail noise that well. Right? So that's why eventually the convergence would be a little bit worse compared to the PI version. However, the PR version is more computationally efficient, right? I only do clipping in each round rather than in each iteration, right? So there's a trade-off in here. Now, so another thing is that we actually we actually can observe that when we set alpha equal to 2, okay? So what happens if you set alpha equal to 2? Well, you can see that all these results will reduce nicely to these results under non-fat tail noise. Okay, so that means that in a sense, these results are of our fat tail algorithms, right? This fat clipping algorithm, they are all like a general extension, like a very natural extensions of the non-fat tail cases. Okay. So now eventually, combining both insights, we can roughly set the following. So if you have a fat alpha moment, okay, then you do our fat clipping, then eventually you can get to optimal convergence rate. Right? That's basically like a key take-home message. So here are some numerical results. Now here, we test the convergence performance of three algorithms: fat average, fat clipping PI, and fat clipping PR. Okay, using some synthetic data, because we want to actually have a better control over the fat tail noise. So here we actually push things to the limit. Okay, they are not, the noise we are using it's not even fat tail. It's actually something even uglier. It's Cauchy. Okay, alpha is less than 1. So well, you can see that. So in here you can see fat average is, failed badly, right? So you can see all the spikes. It's not actually converging. But for both PI and PR, you can see that this green line and the blue line, they're relatively smooth, right? Of course, if you zoom into these two lines, you can actually see that the PI version is still is actually performing better than the PR version, right? Well, of course, with PI you're doing clipping way more often compared to PR, right? So we tested the different alphas, and the trend are all the same. With PI you have a very, very good convergence, but with PR, when alpha is 0.5, right, very, very fat, the tail is very fat, then the PR version is converging a little slower, right? Now, in terms of the catastrophic failure, we actually again tested out, and then you can see that in the non-IID case, right? So most of the time, fat average would have a catastrophic failure, so the success rate is almost 0. With PI and PR, you can see that the success rate gets significantly better, right? With PI, actually the success rate is 100%. Okay, for the PR, it's roughly 60 something. Okay, of course, in the IID case, the trend is also the same. Okay? Now, yeah, just a quick summary. In this work, we study how to deal with the fat tail, which is actually coming from the data heterogeneity, right? And with all this fat clipping, we can manage these fat tail noise pretty well and come up with some beautiful convergence results, and also very nice experimental results. All right, so let me wrap up here. Actually, I'm way over time. So yeah, thank you for the attention. So any question online or locally?
So we are running a little bit over, but maybe we can take a couple of quick questions.
Yeah, we started a little later as well. Yeah, but anyway, yeah. Yeah, I know many our AI Edge colleagues are experts on FL. So yeah, any questions, comments are welcome. Okay.
Doesn't look like there are any. So thank you very much, Kevin. We should probably
actually I have some questions in the local audience. So
oh, okay. Yeah, go ahead.
Yeah, go ahead.
So I was asking if this pattern, like, could this be coming from outliers in our training data?
Yeah, it could. Actually, that's the point. So since in FL you have data heterogeneity, right? You don't have control of the local data set. So the fat tail could be just come from the local data set.
Have you tried using some outlier detection techniques and those optimization methods which are like good at removing outliers while doing the optimization?
Yeah. Well, in fact, you can view this kind of clipping as some kind of outlier, right? I cut off the tail, basically. Yeah. Of course, this is not necessarily the only way, or maybe some other clever ways can also do the job, right? Yeah. I don't rule out the possibility. Yeah. Yeah. Any other question? Oh, I see something in the chat. Oh, so yeah, Doug is actually asking me to repeat the question from the room. So yeah, basically the person in the room asked that could could the noise, the fat tail noise come from the data set, right? So something like that, yeah. So, and basically I answered that's exactly the point, yeah. It's coming from the data heterogeneity of the local data set. Yeah. Okay, any other question? All right, so doesn't seem like we have other questions. So if that's the case, maybe we can, yeah, we can wrap up the seminar today. Yeah. All right, so yeah, thank you all for attending.
Thank you.
Yeah, thank you.